Physics Notes, Unit 27, Diffraction and Interference. Let's start by defining diffraction. Diffraction is the bending of a wave as it passes through small openings or around small barriers. This is a support for the wave nature of light. In a future course, you will explore the particle nature of light, the photonic nature of light, but we're still going to be dealing with waves here. Actually, this is a concept that applies to all kinds of waves. And the nice thing is we can model this with visible water waves. Although most of the problems we'll be dealing with light, but at least you'll have some kind of visual representation of this idea, as opposed to like when we did magnetism and electric fields. That was all ideas and concepts that you had to basically imagine. Even though they're real, they're invisible. But water waves are visible, so we're going to use that as a model here. So these diagrams here, and we've talked about interference before, and I've actually kind of mentioned diffraction before, and we've also talked about the bending of light by refraction. So there's some things that sound similar. Refraction, this is not refraction, okay? Light bending when it goes into a new medium. That was the basis of how lenses work. So we did that unit before, refraction, Snell's law. We've done dispersion. That's the spreading of light into different colors, Roy G. Biv, because blue bends more than red. Now with diffraction, we kind of get the opposite thing. Red actually bends more than blue. The smaller the relative opening, or the smaller the barrier compared to the wave, the greater the diffraction, which I'll show you in some diagrams here as time goes on. Right now these diagrams only have blue. Wow, this is water. It's kind of showing you how in these top three, if you have an opening, this is like an overhead view of waves in a small tank. We have this idea called a ripple tank, a small container of water, and a camera looking straight down. So imagine a small container of water, like about a centimeter deep, a real thin layer of water, and they generate waves or ripples. If you throw a rock in there, well, you wouldn't throw a rock in there, but if you threw a rock into a pond, it would make circular waves. Here we have straight waves coming from the left. So here what we have are straight waves going this way. This would be a ray perpendicular to the wavefronts. But we're kind of looking overhead, like even you could be looking down at waves in a lake, and they would look sort of like lines. The crests of those waves would look like lines. And if you put up two walls there, they're going to call it like they're going to call the hole, the opening, they're going to call it the aperture. Well, some books call it the aperture. And some of the videos will call it the aperture, the opening through which that wave goes. And what happens is once that wave goes through that opening, it bends. The straight part doesn't just make it through, the straight part even bends a little bit. So it may or may not be counterintuitive, but what's the important thing as far as the concept of the bigness or smallness of the opening is that the smaller the opening, like this middle diagram here, you have more dramatic bending. But another way to make the opening look small, like over here in this last one, that opening is the same size as the one on the far left, but the waves are bigger. So there's really two ways to make the opening look small. Actually make a small opening, small aperture, or actually have big waves. So these last two pretty much have the same amount of bending because of the relative size of the wave to the opening itself. Then there's also bending around a barrier. So when you have a barrier, the bigger the wave, the more it bends around the barrier. So there's less bending here with a smaller wavelength. This is useful like with radio waves. You can't see radio waves once again, but it's kind of nice that radio waves can go through things, but they can also bend around things because they're big wavelengths. Radio waves are in a 100, 200, 300 meter, well, AM radio waves at least, wavelengths, so they can bend around buildings, and you can get reception around corners of things because the waves bend around corners. So that's an advantage to this principle when it comes to radio waves. All right, so a lot of this bending, to get really technical, is due to what's called the Huygens principle. And the principle is every point on a wavefront serves as a secondary source. It's a source of secondary, what they call wavelets or waves. They're usually referred to as wavelets. So this basically explains how waves propagate or how they bend around these corners. So what it's kind of saying, and I have a straight wave here. So what I have is a straight wave from A to B. And then you have these points here, these little points that are the source of all these little wavelets. So what they've done is, from this point right here, they've drawn a wavelet like this. I'm highlighting it. And from this point, this wavelet, small little waves. Okay? So from each of those little points, they've drawn a wavelet. And if you keep drawing those, they form the next boundary, this boundary right here, which is basically the progression of this wavefront from A prime to B prime. So it's a linear progression of the wavefront that still maintains a line, as opposed to the second example here, if we have all these points, and I could put more points on here than the ones that are there. But if I take this point right here, that's this wavelet right there from that first point, and then from the second point we have another wavelet, and I can keep going and draw these wavelets. And once again, they define, if you draw those, they define the same shape of wave front as the original wave front. So that shape I just drew, a semicircle or part of a circle, from A prime to B prime is the same curvature, so to speak, to the original wave front, but it's just expanding outward. Anyway, this all lends itself to when a straight wave over here in this final diagram, and by the way, I'm going to change this right now, slit width, they have an A here. When we do these problems, we're going to call this capital D. Capital D. So change that to capital D right now. That's how far apart that opening is, the aperture. So we have waves. What's happening here are there's waves, linear waves that are going this way. We usually aren't going to draw rays like we did with geometric optics, okay, for like finding images for lenses and mirrors. But those arrows just show you the direction of travel of these plane wavefronts, these straight wavefronts. When they hit this opening right here, all those points are the source of secondary wavelets. So bottom line is you get some curvature, especially by the edges. All right. Now, because it's a wide opening for this particular wave, there's not much bending in the middle here. I'll show you some examples. The bigger the wave, the bending occurs by the sides, by where the blockage is, or where the barrier or obstacle is. And once again, the bigger the opening, the less the bending. So let me show you some actual ripple tanks and then some animations of diffraction. All right, so what we have here is basically there's a camera that's pointing down towards the floor. There's a camera like on a ceiling looking into a tank of water, maybe a thin centimeter or 2 centimeters, an inch deep of water in a thin tank. And these white lines are the crests of waves. And there's a source back up here off the page that's sending in plane or straight waves through this opening. And when they come through the opening, they're going to be traveling down towards the bottom here. You can see that they're bent. I'm going to start this. So you can see the waves go through there and they bend, they diffract. All right, let me change it to a different size opening. All right, so now we've decreased the size of the opening, and you can see that there's a much more diffraction here. It's more pronounced. And then back to a wider opening, less diffraction. And back to the moderate one once again. And here's an animation of diffraction. Waves going through a small opening up here or around a barrier. They bend around the barrier and they can even rejoin, especially if the barrier is small. Once again, radio waves can do that. Let me try to start this. Waves bending through an opening or around a barrier, diffraction. So here we go. And the opening is quite wide, so now they're going to make the opening a little bit smaller. So you see a little bit of diffraction there. There we go, smaller opening. More pronounced diffraction. Smaller yet, more pronounced. And another animation, what they're having here is it's kind of like throwing a rock into a pond. So this is supposed to be like a layer of water, blue here. And when you throw a rock into a pond, you get these circular waves. And what they're going to do though is they're going to have two disturbances side by side. So they're going to have two waves that interfere and give you the interference pattern, because that's our end product here, is to see what kind of interference pattern you get when two waves, a very similar wavelength, are interfering with each other. They form a pattern that has an interesting mathematical representation. Single wave. Now they're going to make two waves. And there we go. There's the interference pattern. Okay, so kind of, well, I'm going to show you a real version of this now in a real lake. All right, so what this professor has is he has two balls that he's going to bob up and down in the water. He's going to bob them up and down in the water, creating two similar waves side by side, and they're going to interfere with each other. Now he's just, okay, he hasn't bobbed them yet. So he's going to bob them up and down. He's talking about making them go up and down. Hang on. There you go. So he's bobbing it up and down. Well, that's just one of them. Now he's going to do both simultaneously, side by side. And you'll get an interference pattern of these two waves. Let's see if we can get it here. All right, please work. It's hitching up a little bit here, but you can kind of start to see a pattern there. All right, let me pause this. Oh, there we go. Now, okay, so it's sort of working there. There's the pattern you see of all the waves interfering with one another. And what you hopefully can see here is that there's regions of kind of like cancellation here. That's called destructive interference along this line right here, along this line right here, along this line right here. That's where like crests and troughs are meeting up and canceling out. And in between there's like constructive interference. So we are going to study this mathematically here in a few minutes. And the trick, once again, is going to be trying to draw this type of thing on paper, but it's also happening with light waves, not just water waves. But we can't really see light doing this in the air because it kind of does it in the air, but we're going to shine the light on a screen, and then we're going to have to try to draw this on a piece of paper. All right, quick refresher. This was in the notes a couple units back, but constructive and destructive interference, we're going to only look at the maximum constructive interference. Like, for example, right down here, they have the result is in purple, but you have two waves that are in phase with each other, the yellow one and the blue one, and they make a wave that's twice as tall. And for light, it would be really bright light. That's what we're going to be studying. You'll see bright light. As opposed to completely destructive interference, you would see darkness if it were light. Then you could have anything in between there, but we're not concerned with anything that's kind of halfway between these two extremes. So I'm going to go down in the note. I'm going to skip around in the notes a little bit here. All right, so this is a couple pages forward in the notes, or a page or two down. But this, okay, is just a drawing trying to represent what you saw in that lake with those two green balls that professor was bouncing up and down in the water. And this is pretty much the pattern you see with those wave crests. For light, you don't see the light in the air, but you'll see it on a screen like this. This is like overhead view. It's like, once again, there's like a camera looking straight down towards the floor here. And in the air, unless you put like baby powder in the air, like you see in some of these spy movies, like when they're using lasers and things like that, like the lasers like in a jewelry store that are supposed to be security lasers, or some place where they're trying to, in the casino where they're trying to protect all their money and so forth in the vault. And if somebody breaks the beam, it's like your garage door beam as well. If they break the beam, you can't see it. Because as light travels, it's invisible. Unless you put like smoke in the air, smoke or baby powder or something in the air, then you can see the waves. But light waves don't even look like this when they're traveling, especially a laser beam. It just looks like a straight line. So it doesn't look like it's in the air, but it's this idea in the air. If you shine light, here's an opening here. So you're shining light from the left to the right through an opening. It bends through that opening, all right, and then those waves. In this case, they're already curved, but they could be straight waves. They could be plane waves. Then they hit these two slits. This is a famous experiment called the double slit experiment. Thomas Young did this experiment. And when the waves go through those two openings, it's kind of like the gentleman who was bouncing the two balls next to each other. You get water waves that are circular. Okay? They're circular mainly because, well, it started off linear, but because they went through openings, they bent. They bent twice here. They wouldn't have to bend twice. You wouldn't even need this original blocker over here. You wouldn't even really technically need the first barrier. You certainly need the second barrier. So you have two slits here, and you get interfering. The light interferes. Well, these brown lines here represent constructive interference, where you'd have bright streams of light, and then the blue ones would be dark streams of light. And there's a screen here, which if we're looking down, we can't see the screen. But if we were then sitting in a chair in this classroom, if you were sitting in a chair looking forward at the front screen in the room, so this would be like the overhead view of your screen. Now, if you sat in the chair, you'd be looking straight from the left to the right towards that screen. Here's what you'd see on that screen. You'd see these lines where you'd have constructive interference right here where the maximum is. So that is actually what you'd see on the screen. You'd see a bright beam of a bright streak of light right there, and what we call the central maximum. And then we have a dark spot, and then we have what's called the first order maximum to the left. So this is the center. We have the center bright. These are called fringes, by the way. This is the terminology that we use. Fringes. We have a bright fringe, constructive interference, destructive interference, constructive interference. So you have the central, then you'd have the first order to the left, and the second order to the left, or in our case, going up. But if you were sitting in the classroom looking at this, it'd be to your left, and this would be to your right. But all the spacing would be equal. We'll be studying the math here, calculating the angles and the distances here in a little bit. But that's the idea. This is what you'd actually see on the screen, and it probably wouldn't look white. So let me talk about that. Let me scroll back up here, if I can. All right, so usually it's in color. All right, so here's the idea. That was what I just showed you there was what's called a famous experiment, Young's double slit experiment. He used this basically to measure the wavelength of light. It's based on the principles of diffraction and interference. Basically, everything in this unit is about interference. Diffraction is another major part because the interference is initiated. The first thing that happens here is diffraction. So here, for example, here, this is kind of a sideways. Now you're sitting in the classroom, and now the two slits are horizontal instead of vertical. The one I just showed you, if you were sitting in the classroom, they would have vertical slits. So the pattern on the front board of your classroom would have vertical bright slits, bright fringes, not horizontal ones. But the pattern is in line with the screen. So here we just have two small slits side by side, and the light goes through there. Okay, it's coming through in plane waves. So it's plane waves. Those arrows are the direction of travel, the rays. They hit that opening. When they go through that opening, they bend. It's showing you the bending. And they all interfere out here, but once again, you won't be able to see the interference until it hits the screen. And the bright spot, the central maximum, so you have a central maximum right there, would be a bright central maximum. And then we're going to be measuring angles and distances from there. I'll show you another diagram here in a few minutes. But that would be what so this is basically what you'd see on the front wall of your room or on your screen. Now, here are some, these are vertical. Now, in this case, the slits are vertical. And technically, okay, you'd think, you'd see vertical slits instead of horizontal bright spots, bright lines here, bright fringes. But the laser beam is a small circle. It's only a small circle going through these slits. If it were a bigger, wider beam of red light here, if they spread out the laser light, or they had you don't have to use lasers, but if you had a big source of just red light, monochromatic red light, all right, you'd see vertical fringes here. You'd see vertical, 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 vertical. They would be in the same direction as the vertical slits that the light is shown through. But because they're just little dots coming through, the laser light is a dot. When it enters there, the pattern is small and confined to the dot pattern. And once again, there's a bright central one. I'm not sure. They didn't give me so I don't know which one's the bright central. This is maybe the bright central one right there. And I could have had another constructive one over here. I like to have 2 on each side or 3 on each side, an equal number on each side of the central maximum. So there's always a central maximum, and then you have equidistant bright constructive interference to the left and right of the central maximum. Once again, hang on for the math here. Okay, so this is actual pictures of an actual situation where now this is what you would see like on the front screen of your room, but magnified pretty much. They took a green laser. They took a green laser and they shined it through, say, 2 slits. It actually works if you do 3 or 4 or 5 slits. If you have multiple slits, they call it a diffraction grating. But the math is all the same. For a double slit, it just works better if you have 3 or 4 or 5 slits. But you can prove that the math and the end result is pretty much the same. So we have our central maximum here. So we have, if we just have green light, all right, we have our green light, we have our central maximum. And this run right here is called the first order maximum. And it goes like that. Like this is the second order maximum. Second order maximum. And then third order maximum to the right and to the left as well. This would be the first order maximum to the left, second order, third order. So we're going to be talking about orders. You know, which bright spot from the center. And they're equally spaced. And in this diagram, if they shine white light through those double slits, or it could be triple or quadruple slits. Let's just say it's a double slit. The math is all going to be the same. You shine white light through the middle, and you get this white central maximum, because all the colors interfere constructively in the middle. But what you'll see here is that red is further to the right. It bends more, so it gets a bigger distance from the central maximum. So this is a way to disperse light into its Roy G. Biv without refraction like a prism or a raindrop. So you're getting dispersion here. And I'll show you a little picture later on. They give you these sometimes you go, especially at Christmas time, they give you like these glasses you put on, and when you put them on, you see all these rainbows all over the place. They're what are called diffraction gratings. They're just a bunch of small slits through which light is passing, and the red light bends more than the blue, so it separates. So it disperses, okay, into its Roy G. Biv. And the blue is to the left here. It's not bent as far from the center. The distance from the center maximum to the blue is less. Once again, we're going to calculate that. We're also going to calculate that angle. So blue and then green is moderate, and then red is the most bent. It's the opposite of what happens with refraction. With refraction, blue bends the most. It slows down the most. But with diffraction, red bends the most. It's the biggest wave, so the openings look small. And obviously, you can see here, it gets blurrier and blurrier as the distance goes on from the central maximum. And usually these fade out as well. We'll talk about that. So that's a good actual experiment showing you these interference maximums from the central maximum, what it actually looks like. So they're shining either a big laser light or something that takes up the whole vertical slits. There's vertical slits here. And horizontal slits, you could just turn the whole pattern if you had horizontal slits. And half the problems are vertical slits, half the problems are horizontal slits. It's the same thing. But once again, to draw these on a piece of paper is a little bit challenging. That's going to be our challenge. Oh, here's another example of these fringe patterns. They just took similar slits, say it's a double slit again, and they shined white light through it. So you can see the white pattern here, and you can kind of see the rainbows all blurry there. But if you just take blue light, pure blue light, the spacing there is closer in. Okay, the spacing is closer for the blue than it is for the green, and the red is the furthest spacing. And you'll hear them say things like this possibly in the homework. They'll say, which order of blue starts overlapping the red? For example, if you count like 1, 2, 3, 4, this is the fourth order blue. That's the fourth order blue. Okay, well, if you go 1, 2, 3, this is the third order red. Well, that's the 3 right there. All right. So the fourth order blue and the third order red are almost in the same spot. If I go a couple more, 4, 5, 6. This is the 6th blue and the 7th blue. This is the 4th. Okay, this is the 4th order red. So bottom line is the 4th order red is closer in 1, 2, and then the 6th order blue, because the blue is mostly spaced. So if you superimpose them down here, they start to overlap and blur out. All right, or you can look at the blue versus the yellow. 1, 2, 3, 4, 5. The 6th order blue and the 5th order yellow are almost in the same spot. The 6th order blue is almost as far out as the 5th order yellow. So that's just some of the terminology. And it's the same spacing to the right as it is to the left. But they all start off in the central maximum in the same spot. Okay, so that's a good picture of these fringes, these bright spots, if you use monochromatic light, and how the spacing is. The spacing is equal between each of the fringes. Okay, and that's the diagram I showed you of how that interference pattern is happening along those lines, and then what the screen would look like. All right, so here's the math. All right, so the question is, well, first of all, what is the math, and how are we going to draw these on a piece of paper? All right, so everything I just showed you are what are called interference maximums, constructive interference for 2 or more slits. We're talking about 2 or more slits. For more than 2 slits, okay, the math is the same, and we call it a diffraction grating. I don't know at what point they call it a diffraction grating. 3 slits, 4 slits, I don't know what the definition, but anything more than 2, I will call it diffraction grating. But usually diffraction gratings have like hundreds of slits, closely spaced. They're really close together. They're really, to the naked eye, you can't even tell there's slits there. But here's the math. And what do these things mean? Well, before I get into what that all means, here's a diagram. All right, so little d, well, first I'll talk about what it means. Little d is the distance between 2 slits. So if it's 3 or 4 slits, they got to be all equally spaced. But we'll start with a simple case, 2 slits. If there's 3 slits, they're all equally spaced. But the same math. You just take the middle slit. Okay, so here's what you would see on a screen in the front of your room, but it'd be in color. Like the ones I've shown you, it'd be in color. So they lay this out flat here, but it'd be on a wall. You'd look at it and you see vertical stripes on the wall with these bright fringes. But here's how we draw it on paper. Right here with these bumps. This is, and the reason why we do that is, for example here, this bump right here represents a bright spot. The taller you make that, the brighter it is. The taller you make it, the brighter it is. And what they're showing you here is that the first order here, it's symmetrical on both sides. These first order bumps on either side represent the light is getting dimmer. It's not quite as bright as the central one. In all the examples I showed you, they were all equally bright. So if you were to draw this like what I showed you in all the previous examples, all these bumps here should go up the same height. This would represent all bumps of the same brightness. They're all the same brightness. That's what I've shown you all along here. In reality, there's a lot of cases where they're not all the same brightness. So I chose, for reasons that I'll try to explain here, I chose in the first few examples all bright interference maximums that were all the same intensity, but most of the time they get dimmer much quicker than you saw in the examples I showed you in the previous pages here. So the tallness of those bumps is how bright those are. Now, a couple things here. This example has an X here. Change this to an L. Okay, I'm going to use L. I think the book uses L, but most books use an L there. L is how far you are from the screen, from where your slits are to your screen, and like in the front of your room. I didn't put that down here. Well, L equals screen distance. All right, so I already said D is how far apart the slits are. Theta is the angle when you draw triangles. So for example, if I draw straight to the central maximum and I draw this, they have a dash there, all right, and you measure that distance, and that's called theta. That's the angle to the first maximum. They kind of chop that off right there because that's really on a screen. It really wouldn't be chopped off. I'm going to change a little bit again. I'm going to call this X, not Y. X sub 1, then you have X sub 2. Most books have X, not Y. So I'm using X. I'm also using that down here. Okay, I can put that down here. X, I didn't put it in my notes. X equals the distance between fringes on the screen. Distance between bright fringes. Okay, usually we just measure to the first one from the center, call that 0, and then to the first one here I have X sub 1 here, but they would be equally spaced like I showed you before in all those other examples. They're equally spaced, how far apart those bright fringes are. And like I say, sometimes they're all the same brightness, but sometimes they get dimmer as you go away. A lot of times they get dimmer, as I'll show you. Lambda stands for the wavelength of the light you're using. We like to use monochromatic light. We'll do only one wavelength at a time. You can't do more than one wavelength at a time. Even if you have white light, you have to pick one of the colors to do the calculations, and it'll be different angles for different wavelengths because the bigger red will have a bigger angle than blue will have. It'll calculate out that way. M is the order, how far you are from the center, like the first, second, third. I was writing all those numbers down. Which bright spot you're talking about on that pattern. But this equation right up here at the top is is the most important equation. But there is another equation that your book, well, it kind of develops it in the assignments, but I'm going to develop it for you. For small angles, sine of theta is roughly equal to tangent of theta. It's not exactly the same, but for small angles, and we're dealing with a lot of small angles here. So this is called a small angle approximation. It's called a small angle approximation. Now, what is absolutely true in this diagram, what's absolutely true in my diagram is this equation right here. The tangent of the angle, theta 1, theta 2, theta 3, is my x distance. So if I highlight this in blue over here, up this way, and then I have my hypotenuse. So the base of this triangle, here's the right angle, the base of this triangle is L. That blue triangle that I'm highlighting. The base is L, this is x, and those are at right angle. So tangent is this x over L. Tangent is x over L. And this hypotenuse is, well, you get to use the Pythagorean theorem, and you could do that here, but it would complicate things a little bit. So a lot of times with these problems, because the angles are really small, we don't wave our hands, but we know, you can check it out for small angles, 1 degree, 2 degrees, 3 degrees. Sine of theta is very close to tangent of theta, at least to 2 sig figs. Whoops, I want that to be L. All right. So if you take your d sine theta equals m lambda, which is that red equation that I have circled up above there, and if sine theta equals roughly tangent theta, we have d tangent theta equals m lambda. Well, tangent of theta, I just said, is x over L. See? I'm going to plug that in for tangent. So I'm going to have d times x over L equals m lambda. And if you rearrange that, you can prove with 1 or 2 steps that x, oh, by the way, I'm going to change this, this is going to be an approximate equal, because I substituted tangent in for, I put tangent in for sine. So this is not a perfect equivalence here. It's a close, good enough in most cases, not always perfect, and not, if you have to have better precision, don't use this equation. But there's a couple homework problems where this equation is useful and it'll save you a lot of time. You can do these problems more precisely by just sticking with that first equation and then just doing, not fancy trig, but then using Pythagorean theorem and trig. It just takes you longer. This is a shortcut for problems where they're going to ask you for the separation between the fringes. It'll give you a close enough answer. I give you permission to use this equation. The equation is, if you do this, x, the spacing between those bright spots on that screen is roughly equal to, it's very close to, m lambda L over d, little d. So that blue circle there is useful for some of the homework problems. It'll save you a lot of time. If you want to figure out how far apart, how far it is from the first central maximum, or from the central maximum to the first maximum. The central one we call 0. It's at the 0 location. All right, so that is the math for diffraction maximums. Maximums, the bright spots. All right, so I've skipped several pages ahead here into the sample problems. There's some other things I have to go back and cover. I'll do that in the next page or next session, 27B. But let's apply a couple of those equations those two equations that we just developed there. It says, what is the separation between two slits, okay, for which 630 nanometer light has its first maximum? All right, so this is a pretty much, let me go back to red. This is pretty much a straight plug-in problem. D sine theta, there's really only two equations right here right now, equals m lambda. And we want to find the separation distance d. Well, d is going to be equal to m lambda over sine of theta. So that's pretty straightforward. It's the first maximum. If it said the third maximum, we'd have to put in a 3 for m. So I'm using m for my, which order, which maximum are we talking from the center. The center one's always at 0, it's dead center. But we say number 1, that's the first one to the left or right, or above or below, because sometimes they're a vertical pattern on the wall instead of a horizontal pattern on the wall. But this is a 1 in this case. Straightforward plug in. Wavelength 630 nanometers. Remember, nano is times 10 to the negative ninth. Divided by the sine of the angle. Sine of 31 degrees, 31.0 degrees. So let's just plug it in your calculator. So what is the separation for the two slits? So we have two slits, and if it was 50 slits, that's how far apart each of them are. So it's the slit separation. If you had a diffraction grating, I'll talk more about that in another session. But if you do the math here in this particular part, you end up with D equals, I believe, 1.2 times 10 to the negative 6 meters. They're really close together. So that's the answer. You could say, if you want to be a little bit more professional, D equals 1.2 micrometers. You don't have to do that. Same answer. It's the same. It's actually, the reason why you use these prefixes like that is it saves you time, actually. 1.2 micrometers. Okay, so you can see, the application, the equations look kind of intimidating, but they're really not that bad. Calculate the wavelength of light that produces fringes 7.70 millimeters apart on a screen that's that far from the double slits. And the double slits are separated by 0.12 millimeters. So I can use that second equation now. It says the fringes are that far apart. That's how far apart it could be from the central max to the first order, or from the first order to the second order. They're equally spaced. So x, good enough, we can use this equation. This will save us a lot of time. X equals m lambda L over d. Well, we're looking for lambda. So if xd is roughly equal to m lambda L. You could have just plugged the numbers in. I'm just solving for lambda first. So lambda is roughly equal to x times d over m times L. So our wavelength here, each of these fringes from one to the next, 7.70 millimeters. Be careful here. That's 7.7 times 10 to the negative third meters. You want everything in meters. So that's in meters. X times D. D is how far apart the slits are, 0.12 millimeters. So that's 0.12 times 10 to the negative third. Not 1.2, 0.12. Divided by M, that's just 1. We're just going from one to the next. Times L, how far the screen is from us, which is 2.10 meters. So, hopefully I did this correctly. I got 440 nanometers. 440 nanometers. I ended up with 4.4 times 10 to the negative 7th. Well, 4.40 times 10 to the negative 7th is 440 times 10 to the negative 9th. It's customary to give wavelengths of visible light in nanometers. And once again, all these problems are dealing with visible light. You can actually do this with radio waves or any waves, but light, visible light, is visible on the screen. You see the fringes on the screen, and that's the most common application. So I think it's enough examples here. Let me end. This is Unit 27, Part A, diffraction, bending of a wave through small openings, and then they interfere and give you these diffraction patterns on a screen, and you can calculate wavelengths. That was kind of the purpose of the Thomas Young's double slit experiment. The math gives you then a way to figure out the wavelength of something that's too small to measure with any kind of other measuring device, other than you can measure X and D. Those are measurable with basically with rulers. So there we go. We get accurate measurements for wavelengths of different kinds of light.